Hi, folks. So this is me. I'm Matt Jarvis. I'm a senior developer advocate at Snyk, and I'm joined today by my colleague, Camille Potrek, who's a senior security engineer at Snyk.
Hi, everyone.
So today's talk is going to be about kernels. So let's start with making sure that we have a shared understanding of what a kernel is. We're going to be pretty generalized here because there are a variety of ways that these things work, but it's definitely not either one of these. When we talk about operating systems, we're describing the core software that provides the interface between the computer hardware and the end user. And whilst operating systems may ship with end user applications in them, in the computer science sense, we're talking about the programs that enable applications to run on the hardware. And this would usually consist of the operating system kernel and various utilities and libraries that perform the base functions of operating the computer. And the kernel of the operating system is right at the heart of this. It's the first thing that's loaded by the bootloader when the computer started, and it's always resident in memory. The function of the kernel in general is to handle interactions between software and hardware. So everything from managing the CPU downwards, reading and writing from the disk, handling packets on the network, all that kind of stuff. This is a slightly old diagram, but fundamentally this is how the boot process works. So we have the BIOS. This is firmware, lives on the motherboard, and it's the first thing executed by the CPU when it powers up. This BIOS then looks on the various disks that might be configured, looking for a master boot record. And if it finds a partition labeled bootable in the master boot record, then it will load the boot sector code from that partition, in this case, a bootloader, grub, and the bootloader will then load the kernel, boot the kernel. Once the kernel's running, that then will load an initialization daemon, which then handles all the startup of the other system software, and the system is then up and running. And if all of our applications directly access the hardware, then you can imagine that things would get very complicated and the potential for things to go wrong would be huge. While some historical computers used to work like this, in general, they ran single applications. So there really wasn't any need to manage access. And in this way, you can think of the kernel like a traffic controller. It's directing requests down to the hardware in the right order, synchronizing actions and keeping the flow of information happening all the time. Modern operating systems are multitasking. So the CPU switches between applications to keep them running all of the time. Now, this happens so fast that it's invisible to the end user, but this switching's going on continuously. What actually happens is that as each process needs time from the CPU or to interact with something, the kernel basically saves the program state into these process control blocks, these PCBs, switches to the new process, executes what it needs to do, saves that state back into another process control block, and then switches back to the original process, reloading its state from that first PCB, and so on. And operating systems in general separate their memory into kernel space, which contains the kernel, things like device drivers, and user space, which contains all of the other running applications. And the processor prevents applications from accessing kernel space or each other's memory. And this is the basis for memory protection, so stopping programs stomping all over each other. But it also enables privilege separation, allowing different things to have different permissions to do things inside the operating system. In general, applications don't talk directly to the kernel. Instead, the kernel provides an abstraction layer for applications to access, known as the system call interface or syscalls. This provides a way for applications to ask for things like writing to the disk or sending packets over the network. When an application performs a syscall, the CPU will make the switch from user space to kernel space in a mechanism that's known as context switching. And the kernel will then execute the syscall, and the CPU will switch back to user space, returning data to the application, whatever resulted from that syscall. Every time the kernel does this, it needs to check if the process is actually allowed to ask for it to perform that action. And behind the scenes, the kernel maintains a list of processes together with a set of allowed capabilities or permissions that the process has. This is represented in the kernel as this data structure called struct, which looks like this. And this structure contains a ton of information about the process, including its PID, its JID, and the priorities it should be allocated. And it also contains references to these credentials data structures, which are the ones which set what things the process is allowed to do. This is defined in the kernel headers, and it defines sets of capabilities or kernel level permissions which the process is allowed to execute. There are various sets of these capabilities defined in the kernel, which depend on the way the process is launched, but fundamentally they're all defined in this data structure. So every time a process asks to perform a syscall, the kernel will look up this structure and check if the process is allowed to do so. So over to you, Camille.
Thanks, Matt. So as Matt just described, there is this credential structure in kernel memory that manages what user permission belong to the process. In privilege escalation, our goal is basically to replace the current value, which represents our current user. In this example, a integer value 1000 to a more privileged user. 0 represents root user on a Linux kernel system, which is basically the target we're aiming at. Let's start by just describing in a high level what's the process of privilege escalation. Our first step is to identify a vulnerability. These are examples of vulnerabilities in the Linux kernel that happened in the past few years that all led to privilege escalation. They impacted everything from network stack to eBPF processes. You can find examples of exploits on some of these websites: Exploit Database, Rapid7, and Packetstorm. Now that we know we have a vulnerability, we need to have a way to reach it. There's numerous ways from kind of process user space point of view we can reach kernel code. These are syscalls, network packets, and BPF programs. Usually when we reach a vulnerability or a bug in a code in a kernel, that leads to a fatal exception that leads to a crash of the system. So in order to make use of vulnerability that we can reach, we need to be able to control kernel's behavior after the kind of exception is hit. There is a number of controls in Linux kernel that make this process difficult. Supervisory memory execution and access prevention mechanism basically stop us from executing or accessing certain memory locations. There is a memory randomization system that kind of shifts around internal function addresses within the kernel. There is a page table isolation, which makes it difficult for us to access user space memory from kernel and vice versa. And beyond the specific security controls, there are general state machine operation that override memory continuously in Linux kernel, like scheduler and memory management units. And finally, if we managed to reach a vulnerability, control the execution after we've hit the exception, we need a way to return the control to the caller. In our case, it could be creating a shell on operating system or returning a network connection to our remote control system. So in our demo today, we have used an Ubuntu Linux distribution that runs our node pool of Kubernetes cluster. We've deployed Kubernetes with Ansible provider, and we're using Docker as our runtime system. In order to kind of link all of these things together, quick reminder of how pods link to processes in kernel. Linux kernel does not have a concept of a container. Everything in Linux kernel is a process that is represented by the task structure that Matt has mentioned before. Container is an abstraction on a runtime level that uses namespaces, C groups to kind of isolate processes from each other. Pods on Kubernetes are composed of one of many containers, and operating system and Linux kernel is a common thing that runs in all of these abstractions. So in our demo, we're going to be using an old vulnerability that was patched in 2017. In this vulnerability, there is a signedness issue, which allows us to overwrite memory on a heap when we send an invalid size of a buffer. This was patched some time ago, and you can find details of this exploit on a GitHub link provided. In order to reach this vulnerability, however, a user needs to have permission to create raw network packets. That permission is usually not granted to unprivileged users. However, we can use a feature in Linux kernel distributions that allow us to create unprivileged user namespaces. These create containers that kind of grant us all of the capabilities without limited space, which then in turn allow us to reach this vulnerability. In order to privilege escalate in our exploit, we're going to use a common pattern. Linux kernel uses functions such as commit creds and prepare kernel creds to manage internal permissions within the memory. If we know internal addresses of the kernel, we can reuse these functions for our benefit during the exploit and reassign the root permissions to our task. So on our first demonstration, we're going to show you how the exploit behaves on a host system without any containers. So what we've prepared here, we have a Ubuntu node. We're running as a user called dev with UID 1000. We've created a simple flag that is only accessible to a root user to demonstrate our target when we successfully exploit the system. We're going to run our exploit. It runs very fast. It grants us root permissions. And what we should see here is that we are root user. And just to make sure, we're going to read the exploit. So this is how quickly it works on a host itself that doesn't have any containers running. All right. Now we're going to demonstrate how the same exploit is going to work on Kubernetes. What we have here is a pod specification. We have configured this pod with some security controls. So we're enforcing that the pod is going to be running with user ID 1000. We're setting that privilege escalations should be prevented within the container itself. And we also are dropping all of the capabilities from the container to make sure that any potential vulnerabilities cannot be exploited. So let's see how our exploit behaves now within this container. I'm going to show you the pod specification again. There is our security context settings. Making sure we're dropping all the privileges. We're mounting a flag as our target within the container. And now we're going to simply execute a shell in this pod. You immediately can see that we running as user 1000 and we have no significant permissions within the container. There is the flag that we mounted. We should not be able to read that contents of that flag. That's the case. What we're going to do is exploit the container again. And as we can see, our exploit appears to be working. We have root credentials. We can read the flag that's mounted in our namespace. What we're going to do next is see if we can see other files on the root file system that we expect the root user to be able to see. And we're also going to check the network interfaces. We see that we still only see what's allowed within the container. So let's understand why is that the case. in order to understand why we were unable to see the actual host network interfaces, we need to dig a little bit deeper into Linux namespaces. There is 8 Linux namespaces. We're going to only touch on 4 that are relevant to this exploitation process. Mount namespace separates the file system permissions that we can see. This allows us to have this abstraction and not see the file system that belongs to the host. We can limit it to what's in the container. Process namespace isolates the view of the process tree. Whenever we create a new container, the initial process becomes the root of our tree, and therefore we cannot see what's behind it. Only the host operating system and the kernel can see all of the processes. The network namespace isolates the network devices that we have access to, and this is what prevented us from seeing the physical devices on our host. We were still only able to see virtual interfaces in our container. And finally, there is a user namespace, which isolates the security credentials of the system. This links directly to what capabilities the user has in the current namespace. So our next goal, in order to fully exploit the container and gain access to our host operating system, we need to switch the namespaces that the container is running in. As we previously described, there is a credential struct that holds user IDs. The same struct contains information about which namespaces our process belongs to. And our goal in the next exploit is to overwrite the existing namespaces with the host root namespaces pointers. In order to do that, we need to make use of more functions that are available to us within Linux kernel. As before, we used the kernel credentials functions. Now we're going to use functions such as switch task namespaces and set ns, which allows us to override these namespace pointers. So take 2 of the exploit. In green, you see additional steps that are required in order to successfully privilege escalate from a container to a host operating system. So we've upgraded our exploit. We've added additional functions to make sure we overwriting our namespaces, and let's see how that behaves in a container. We've added additional flag that we're not going to mount within the container that only can be read by a root file system. As you can see on a node, we cannot access these. So we've executed a shell in the same container. As you can see, flag.txt is not there. It's hidden from view because of the mount namespaces. And now we're going to exploit this container with improved functionality. We can see that we are root again. However, immediately you can see that we can see more files. The mount namespace has been switched, and we can now see all of the host files from within our container. And we are root user, which means we can read all of the file systems on the host. We can also see all of the network interfaces, which means we correctly switch the network namespace. And we can see host processes, which means we successfully exploited the processes namespaces as well. So let's talk about a little, how can we further protect our containers? Capabilities allow us to provide granular controls to kernel functionality. However, they are limited in that the system calls need to expose capabilities. Some system calls are still accessible regardless of your capabilities configuration. Seccomp is another security protection that we can use to filter calls to the system calls. The improvement over capabilities here is that you will not be able to reach the system call in the first place. So it doesn't matter if capability allows it or not, you won't be able to enter the system calls because of the filter. And finally, we have Selinux and Apparmor. These are mandatory access controls. These are additional layers of protection you can apply even to root users in order to protect the kind of user space controls. So for example, you could prevent root user from reading certain files, and they wouldn't be able to disable that unless they reboot the system and disable these mandatory access controls in the first place. So here we have a pod specification when we enabled a Seccomp profile. Default profile in our runtime prevents all of the dangerous system calls that are allowed. So let's see how our exploit behaves in this more secured pod. What are we going to do? We're going to run exactly the same exploit in our more secure pod. We're going to see the pod spec once more, just to make sure we have the correct annotation set. As you can see, we're now going to enable a Seccomp filtering on this container. Just to make sure the pod is running. Once again, we're going to execute a shell. You see, we are user 1000. We cannot access the file permissions. We're going to run an exploit. As you can see, we immediately fail our exploit. The reason being, we cannot enter the clone new user system call anymore. This specific system call does not require any capabilities, and it's not protected through capability limitation. However, Seccomp can protect us a layer above and prevented us from executing this specific dependency. So what else we can do to protect our systems? Everything we showed you so far is a stopgap solution. Whenever you have vulnerable code running in your kernel, always patch. Accept all the patches from kernel maintainers and patch your systems. Maintain your deployments as kettle, not pets. Whenever you have issues, you need to upgrade, simply deploy new versions of the previously running deployments. And finally, as on this speech, no shells. Try to limit accessibility to your containers. Try to run kind of hands-free administration, use CI/CD pipelines, and limit ability to execute interactive commands. So there's alternatives to containers. Lightweight hypervisors allow you to run your pods, your containers within limited kernels. So like in our demo, we used a shared kernel between all of our deployments. Kata containers and Firecracker are examples of solutions that provide a layer of kernel that runs specifically for your pod, which means if your hypervisor is vulnerable, the exploit from container won't be able to reach the vulnerable code paths and stop you before you can even exploit it. gvisor is alternative solution that kind of provides abstraction layer and simulated kernel environment, which should protect you from a generic exploits like in this demo.
So, as we've seen, these kernel level exploits are very powerful, and they've got the potential to escape our containerization. And as Camille said, the only real weapon we've got against this is to upgrade our kernels and to make sure we're using Linux security module implementations like SELinux or Apparmor. Luckily, this type of vulnerability is fairly rare in comparison to more common application level vulnerabilities. And the security context settings in our Kubernetes configuration provide us with settings that can reduce the blast radius of an exploit if our containers or our pods do get attacked. So don't run your containers as root, disallow privilege escalation, and always follow that principle of least privilege. Start by disallowing everything, dropping all capabilities, and then work your way back to finding the minimum set of capabilities that your application requires. And Snyk can help here by scanning your Kubernetes YAML and detecting insecure settings that could contribute to exploits in your pods before your containers are deployed to production. So thank you for listening, and you can sign up for free at snyk.io/signup.